Welcome. This week we're going to be talking about propositional logic. Now, in the introductory video for this course, we talked a lot about how important mathematical reasoning is for computer scientists. It's what allows us to say things about the correctness of programs that we might write and analyze the complexity and runtime of an algorithm that we might deploy, and in general, to say things about the well-posedness of problems that we might like to solve as computer scientists. Now, in this series of lectures, we're going to go all the way down to the foundation of mathematical reasoning, which is propositional logic. Propositional logic is what gives the precise meaning to mathematical statements and allows us to differentiate and identify and distinguish valid versus invalid mathematical arguments. So the basic building block of logic is what's called a proposition. A proposition is a declarative sentence that is either true or false, but not both, and not either. So, for example, the following four statements are all propositions. Boulder is a city in Colorado. Boulder is the capital of Colorado. 2 plus 2 is equal to 5, and 2 plus 2 is equal to 4. Now, if you look at those, some of those may seem different from others to you, especially if you've ever been to Colorado. In particular, 2 plus 2 equals 5 seems a little bit fishy. But the important thing to remember is that a proposition just has to be a statement that you can say is either true or false. Regardless of whether it is true or false, the fact that we can say that is what makes it a proposition. The actual truth or falsehood of a proposition is what we call the truth value. So we say that the truth value of a proposition is true, and usually to shorthand it, we denote it with a T, if it is a true proposition. And the truth value of a proposition is false, and usually we denote that in shorthand with an F, if the proposition is false. And so, for instance, if we go back up to our four examples, Boulder is a city in Colorado is in fact a true proposition. I'm sitting in it right now. On the other hand, Boulder is the capital of Colorado is a false proposition because Denver is the actual capital of Colorado. 2 plus 2 equals 5. I think hopefully we will all agree that that proposition is false. And similarly, 2 plus 2 is equal to 4. We can probably agree that that is true. Okay, so those are examples of propositions. And now let's look at some things that are not propositions. So here are four examples. Study hard. When is the homework due? X plus 1 is equal to 8, and X plus Y is equal to Z. So if we look at these one by one, study hard is kind of more of a directive or an instruction or something like this, but it's not a proposition, because if I just told somebody study hard, I don't think they would think that that was either a true or a false statement. It's kind of a directive. Similarly, when is the homework due is a question, and it does not have any particular truth value. And the third and fourth examples are a little bit more subtle. So for instance, X plus 1 is equal to 8. Without knowing what X is, I can't say anything about the truth or falsehood of that statement. Now, if I were to set a particular value of X, if I were to say that X is equal to 7, once I do that substitution, then this would in fact become a proposition, but in its current state, where I haven't defined what X is, it is not itself a proposition. Similarly, in the fourth example with X plus Y is equal to Z, for certain values of X, Y, and Z, this would be a proposition that may be true or false, but in its present form, without specifying values of X, Y, and Z, it is not itself a proposition. Okay, so a lot of times when we're doing kind of propositional logical algebra, it gets a little bit hairy if we are doing or writing propositions in their full kind of English statements or even mathematical statements. So a lot of time what we do is we replace certain propositions with lowercase letters, usually P, Q, R, and S are popular ones. And so for example, I could say let P represent the proposition Boulder is a city in Colorado, and I could let Q represent the proposition 2 plus 2 is equal to 5. And then I could just talk about the symbol that represents that proposition and its respective truth value. So for instance, I could say, in this case, where P represents Boulder as a city in Colorado, I would say P has a truth value of T or true, because that is in fact true. And I would say that Q has a truth value of F or a truth value of false, because 2 plus 2 does not actually equal 5. Okay, so now what we want to do is we want to take some of these kind of simple atomic propositions like P and Q, and we want to start modifying them and combining them in fancy ways so we can say more interesting things. So the simplest modification that you can do to a proposition is you can negate it or take the negation of it. So if the symbol P is a proposition, the negation of P is denoted by putting this little kind of a minus sign with a little crook on it. And it's the statement, it is not the case that P. So the truth value of not P is kind of has the opposite truth value of whatever the truth value of P is. So for example, if I let P denote the proposition that Denver is at least 5,000 feet above sea level, the negation of P is the proposition, it is not the case that Denver is at least 5,000 feet above sea level, which just throwing it is not the case that in front of a proposition is a little bit kind of clunky, but there are a lot of other kind of English statements that are equivalent. So an equivalent thing would be something like Denver is at most 5,000 feet above sea level. Okay, and so if you take a proposition P and you negate it, the negated proposition always has the opposite truth value of the original proposition. So in this case, P denotes the proposition that Denver is at least 5,000 feet above sea level. That's of course true because Denver is the mile-high city. It's roughly 5,280 feet above sea level. So we would say that P is true. And now the negation of P, the sentence that we've written below here, that Denver is at most 5,000 feet above sea level, this then, of course, is false because Denver is more than 5,000 feet above sea level. Yeah, so when we start modifying and combining propositions, a lot of times we want to kind of analyze the possible truth values that it could occur. And we do this using a device called a truth table that is just a nice tabular method of keeping track of everything in a nice succinct way. And so generally the strategy is that you start by taking your atomic or simple propositions. In this case, for the negation, we only have P, and listing all possible truth values of P. And then in a separate column, you list the compound proposition that you would like to know the truth values of. And then you kind of just go through. And for instance, this is the truth table for the negation of P. In the first column, I'm assuming that P is true. And so since the negation of P flips the truth value of P, that means that the negation of P is false. And in the second column, I'm assuming that P is false. And then the negation of P flips the truth value back to true. And now I have a nice summary of all of the possible truth values of the negation of P, given all of the possible truth values of P. So now we'll start combining multiple propositions in interesting ways. Two propositions can be combined using logical operators called connectives. And some of those that we'll talk about are below. They're the conjunction, which represents an and relationship and is denoted by this kind of upside down caret sign. The disjunction, which represents an or, and it's denoted by this kind of V shape. The conditional, which represents if-then relationships, and it's denoted by an arrow pointing to the right. And the biconditional, which represents if and only if relationships, and it's denoted by an arrow that has kind of a double arrowhead on the left and the right. So today we're going to talk about the first two, conjunctions and disjunctions, and next time we'll come back and we'll talk about conditionals and biconditionals. So we'll start with the conjunction. So suppose that P and Q are any two propositions. The conjunction of P and Q, which is denoted by P in the upside down wedge Q, is the proposition P and Q. And in particular, the conjunction P and Q is true in the case when both P and Q are true and false otherwise. So for example, let's suppose that I say the proposition, today for lunch I had a cheeseburger and I had a soda. Now, this is kind of a conjunction of the two propositions that are today I had a cheeseburger and today I had a soda. And so let's just say today for lunch I had a cheeseburger is P, and today for lunch I had a soda is Q. Now, if I were to say this to somebody, and it was in fact the case that today for lunch I had a cheeseburger and today for lunch I had a soda, then we would say that this was a true proposition. On the other hand, if even one of the two conjuncts, so when I say conjuncts, I mean the two things that I'm putting together in the conjunction, if either one of the two conjuncts is false, then I would say that this entire proposition is false. So let's suppose that for today for lunch I did have a cheeseburger, but instead of a soda I had milk. So I think we would agree that if that were the state of affairs, and then I told you that today for lunch I had a cheeseburger and I had a soda, you would tell me that proposition is not true, that proposition is false, because both of the two conjuncts were not true. Here's another example. Chris is fine, but his neighbor Tony has the flu. So this is again a conjunction. It looks a little bit different, but if we look at it, we'll see that it's a conjunction of the proposition Chris is fine. So let's call that P. And his neighbor Tony has the flu, and let's call that Q. And so together this represents, or this is represented by the conjunction P and Q. Now, this looks a little bit different because it doesn't actually use the word and in it anywhere. In fact, it uses the word but. But if you think about it, but is actually a conjoining word. It's just an artifact of the English language that we use but when somehow the two things that we're conjoining are in some sense in odds with each other. That doesn't make it any less of a conjunction. It's just kind of a quirk of the English language. All right, so the next thing we'll do is we'll write down the truth value, or the truth table for the conjunction of P of Q. So pretty much the same process as before. I'm going to make columns in my truth table that have all possible truth values of all of the simple propositions involved. In this case, this is P and Q. And then we'll make a column in the truth table for the conjunction P and Q, and then we'll write down the associated truth values. Now, notice that there are more rows in this truth table than there were in the negation truth table, and that's because now I've got two different conjuncts. I've got two different propositions, P and Q, that I need to combine. And so this is kind of the standard way to write a truth table if you have two simple propositions. To get all possible combinations of it, one thing you can do is for the first proposition, P in this case, you can start by listing true, true for the possible truth values, and then list false, false at the bottom. And then for the second column, you alternate true, false, and true, false. And this guarantees that you get all of the possible combinations of truth values of P and Q. Okay, so we just need to fill out the truth table. And if you remember, our definition of the conjunction said that a conjunction is true only in the case that both of its conjuncts are true. And so if I start looking at the rows of the truth table, the only place that that happens is in the first row. And so in the first row for P and Q, I'm going to write a true. And now, for instance, for the second row, because P is true and Q is false, they're not both true, so I'm going to write a false for the conjunction. And similarly for the third row, P is false, so the conjunction must be false. And then in the final row, they're both false, and so certainly the conjunction is false. Okay, so slightly different from a conjunction is something called a disjunction. So let P and Q be propositions. The disjunction of P and Q, which is denoted by P and the V sign Q, is the proposition that represents P or Q. So the disjunction P or Q is false only when both P and Q are false, and it's true otherwise. So for example, let's suppose I have the proposition, students who have taken linear algebra or prob stats can take machine learning. So if I think about students who have taken linear algebra as being a proposition P, and a student has taken prob stats as a proposition Q, then the first part of the statement, a student has taken linear algebra or prob stats, is a disjunction because it's an or of the two individual propositions a student has taken linear algebra and a student has taken prop stats. Now, in particular, this kind of disjunction is what's called an inclusive disjunction, in the sense that it's fine if both P and Q are simultaneously true. Certainly in this case, if you were trying to evaluate somebody's preparedness for taking a machine learning class, if it happened to be the case that they had taken both linear algebra and prob stats, we would not say that they were banned from taking machine learning. That would be totally fine if both of the disjuncts, in this case, were true simultaneously. Okay, so the truth table for the disjunction looks as follows. Notice that my columns of possible truth values for P and Q look exactly the same thing, or exactly the same way that they did in the case of the truth table for the conjunction. And so now I start filling out my column for P or Q. And remember that a disjunction is true if either or both of the two disjuncts are true. And so in the first column, both P and Q are true, so the disjunction is true. In the second column, P is true, and that's enough to make the disjunction true. In the third column, Q is true, so that makes the disjunction true. And then finally, in the fourth column, neither P nor Q are true, and that makes the disjunction false. Okay, so in the previous example, the inclusive OR made perfect sense. We didn't care if a student had taken both linear algebra and probability and statistics. But in certain cases, that inclusive disjunction or that inclusive OR is not quite right. So for example, let's suppose that you're in a restaurant and you order a burger and the waiter tells you the burger comes with either fries or a salad. Now, if you were to turn to your waiter and say, I'll have the fries and the salad, he would probably look at you funny and probably try to charge you a few dollars extra, because that's not what they mean when they say that you can have fries or a salad. So in this case, this is an example of what's called an exclusive disjunction or an exclusive OR. So again, if P and Q are propositions, the exclusive OR of P and Q, which we denote by P and then this circle with a plus sign through it, Q, is the proposition that is true when exactly one of P and Q is true and false otherwise. Or another way to say that is the exclusive OR of P and Q is false when P and Q are both false, and it's false when P and Q are both true, and it's only true if exactly one of P and Q are true. So if we write down the truth table for this, in the first row where P and Q are both true, then the exclusive disjunction is false. Remember, that's the big difference between the exclusive and the inclusive disjunction. In the second row where P is true and Q is false, the exclusive disjunction is true. In the third column, when Q is true and P is false, the exclusive disjunction is true. And in the last column, when P and Q are both false, or excuse me, the last row, when P and Q are both false, then the exclusive disjunction is false. So if you look at the truth table, notice that another way that we can think about the exclusive disjunction is that it's true exactly when P and Q have opposite truth values. Okay, so let's summarize our single conjunction and our two different flavors of disjunctions. And so here's the truth table for all three of them again. And so for the conjunction, remember that this is only true in the case where P and Q are both true and false otherwise. For the inclusive disjunction, it's only false when both P and Q are false and it's true otherwise. And for the exclusive disjunction, like we mentioned on the previous slide, it's true when P and Q have opposite truth values and it's false all of the other times. Okay, so now we've got these three kind of basic logical connectives, the conjunction and two flavors of disjunction at hand, and we also have negations. And so now what we can do is we can start combining those four things in really interesting ways. So for example, we might want to analyze the truth value of a compound proposition that looks like this. And so notice that we've combined some things here. And so here I have the disjunction P or Q. And then I've taken the negation of that entire thing. And notice that I've put parentheses around P disjunction Q because I want to be really clear that I'm negating that disjunction and not just one of the two disjuncts. And then we have that entire statement, and then I combine that entire compound proposition with the conjunction with Q. And so now we might ask, what are the possible truth values of this compound proposition given all of the possible truth values of P and Q? And of course, we would analyze that by making a truth table. Now, here's the trick to doing a truth table for complicated compound propositions. The first thing I'm going to do is I'm going to break it up into its smaller parts, and then I'm going to build a truth table column for the simpler parts and then kind of slowly build up to my more complicated proposition. So if I look at this, I already have a column for Q. That's sitting over here because that's one of the simple propositions. The next kind of simplest thing involved is going to be this disjunction between P and Q, so P or Q. So what I'm going to do is I'm going to start by filling out the truth table for P or Q, and then once I've done that, if I want to know the truth values of things that involve P or Q, I've already got this kind of nice summary of what those truth values are. So this is just the truth table for the disjunction P or Q. And remember that this is false only when both P and Q are false and it's true otherwise. So the first row, P and Q are both true, so the disjunction is true. It's true, so the disjunction is true. The third row, Q is true, so the disjunction is true. And then in the fourth and final row, P and Q are both false, so the disjunction is false. Now the next thing I'm going to do is build up to kind of the next bigger thing in the compound proposition, and that's going to be when I include the negation on this disjunction. And now the nice thing is I already have the truth values for P or Q, and so to negate P or Q, all I need to do is look at my column for P or Q and flip to the opposite truth value. So the negation of P or Q, if I look over here at my P or Q column, is I just have to go through and flip these truth values. So P or Q in the first row is true, so its negation is false. In the second row, P or Q is true, so its negation is false. The third row is again true, so its negation is false. And in the final row, P or Q is false, so the negation of it is true. And now I'm almost there, because now I'm just going to include the conjunction of not P or Q with Q. And so to do this, and then I'll be done, to do this, I've got this nice column for not P or Q. And I've also got my original column for Q, which is over here. And now I just have to take the conjunction of those two. So remember, the only time that a conjunction is true is if both of the conjuncts are true. So I'm going to scan through the rows of this. And if the truth values in those particular columns are both true, I'll write a true, and if at least one of them is false, then I'll write a false. So in the first row, Q is true and not P or Q is false, so their conjunction is false. In the second column, Q is false and not P or Q is false, so their conjunction is false. In the third column, Q is true and not P or Q is false, so their conjunction is false. And in the last column, Q is false and not P or Q is true, but since Q is false, their conjunction is false. And so now I know for all possible combinations of truth values or P of Q, the potential or possible truth values of our compound proposition that we were trying to analyze. Okay, so the next thing I want to do is kind of a fun application. And this is a particular logic puzzle that pops up all over the place in propositional logic called a knights and knaves puzzle. So the idea is that there's a mythical island, and on this mythical island there are two types of inhabitants. There are people that are knights who always tell the truth no matter what they say, and knaves who always lie. And so the idea behind a knights and knaves puzzle is you're walking on the island and you encounter some people and they tell you things, and your goal is to try to figure out what the nature, by that I mean whether they're knights or knaves, of each of the people are just by the things that they say. So for example, you encounter two people who will very originally call A and B, and A tells you B is a knight. And then B tells you the two of us are of opposite types. And so now our goal is if we can we figure out what types of people A and B are. And so there are lots of ways to solve problems like this, but we're going to use a truth table. And so what we're going to do is we're going to consider all of the possible combinations of the types of people that A and B could be. And we're going to see if that can kind of convince us of particular natures for A and B. And so the way that we're going to start this is we're going to assign symbols to the propositions that A is a knight and that B is a knight. So I'm going to let P be the proposition that A is a knight, and Q be the proposition that B is a knight. And so now the nice thing about this is that if I say let's assume that P is true, then that means that we're assuming that A is a knight and that anything he says should be true. On the other hand, if I say let's assume that Q is false, then that would say that B is not a knight, or in other words, B is a knave, and that anything that he or she says should be a lie. And so I'm going to denote the first two columns of my truth table by P and Q, which are the statements that A is a knight and B is a knight. And the next thing I'm going to do is I'm going to translate A's and B's respective statements into a compound proposition based on P and Q and based on what the two people said. So if we start with A's statement, A tells you that B is a knight. And so symbolizing this statement is particularly easy because we already have a symbol for the proposition B is a knight. It's exactly Q. And so that would be how we would symbolize A's statement. And B's statement, which was that the two of us are of opposite types, that would be the statement that P and Q have opposite truth values. And if you remember, we had a nice logical connective that captured that, and that was the exclusive disjunction of P and Q. And so now what I'm going to do is I'm just going to create two columns in the truth table corresponding to those logical propositions, and then this looks like this. And the next thing I'm going to do is just fill out the truth table, and then after that we'll talk about how you can use the filled in truth table to determine the natures of A and B. So the truth table for what A says, which is just the proposition Q, is very easy. I almost don't need a column for it because I'm just going to copy the truth values from the Q column. So I get true, false, true, false. And now for the exclusive disjunction of P and Q, the translation of the statement that B made, I just have to write down the truth table column for the exclusive OR. And so if you remember, the exclusive OR was true when exactly one of the two propositions was true, and it was false if either of the propositions had the same truth value. So this gives me false, true, true, and false. Okay, so now I'm ready to kind of analyze this truth table and see if this can kind of lead me to the solution of the puzzle. So the question that I'm going to ask is there or are there a row or rows where A and B's type or their nature, that is whether they're knights or knaves, makes sense with the truth value of the statements that they made? So for instance, just as a hypothetical, let's suppose that P was true. If P is true, since P was the proposition that A is a knight, then we would expect anything that A says to also be true. On the other hand, if Q is false, which means B is a knave, then we would expect that anything that B says to be false. Okay? And if we find an instance or a state of affairs in the truth table where that doesn't work, so suppose Q is false, meaning that B is a knave, but something that B says is true, well, that can't possibly be right because that does not jive with the definition of what it means to be a knight or a knave. So what I'm going to do is one by one, just moving from person to person, I'm going to go through the truth table and I'm going to highlight the rows where that particular set of truth values is consistent with the nature of A. Right? And so for this exercise, I'm going to look at, I'm only going to care about the column corresponding to whether A is a knight or a knave, and the column corresponding to what A says. Right? I'm going to completely ignore B for this part of the exercise. So I'm going to go through this, and in the first row, we assume that P is true, so that means that A is a knight. And if I look at the truth value of what A said, that's also true. And that's good, that's consistent, that's something that could possibly happen. Alternatively, if I look at the second row, where P is true, which means A is a knight, and I look at the corresponding second entry for the truth value of A's statement, it's false. And I know that this is inconsistent, this can't possibly happen, because if it's really the case that P is true and A is a knight, then it wouldn't be possible for the thing that he said to be false. Okay? And so what I'm going to do is I'm just going to cross out this row in the truth table, because I know that this could not possibly work. So now I'm going to move on to the third row. And in the third row, P is false. And so that means we're assuming that A is a knave. And if I look at the truth value of a statement, it's true. And again, this is not consistent. This is not possible because if A was a knave, then the thing that he said couldn't be true. And so that means that this row for A is no good. And then finally, let's look at the last row. In this case, P is false, so A is again a knave. And the thing that he or she said is false, and that's consistent because if A was a knave, then what he said would also be false. Okay, now what I'm going to do is I'm going to go through and I'm going to do the same analysis, but only looking at things involving B. So in this case, I'm going to look at the column for whether B is a knight or not, so the truth values of Q, and then I'll look at the column for the statement that B made, which was P exclusive or Q. And I'm going to do the exact same thing. I'm going to check the consistency of B's nature with the statement that he or she made. So in the first row, Q is true. That means that B is a knight. But in the associated column for what B said, I've got a false, and that's inconsistent because if B was a knight, then he or she couldn't have said anything that was false. And so I know that this row doesn't work. And it's actually not necessary to do this, but we're just as an exercise, we're going to check the second and third rows just so that we get more practice. But so in the next one, I've got that Q is false, meaning that B is a knave. And then if I look at the truth value of what B says, that's true. And so again, that's inconsistent, and were this row not already crossed out, I would cross it out again. And then in the third row, I've got Q is true, which means that B is a knight. And in the associated column for what B said, I've got a true, which means what B said was true, and that's consistent, and that potentially could be a solution, except for the case that we've already crossed it out for A. And then finally, we'll look at the last row. In this case, Q is false, and so B is a knave. And if I look at the corresponding thing under what B said, that is also false, and that's consistent, and so that row is okay. We haven't found any contradictions, and so that could be a solution. And so if I look at my truth table now, I want to look for rows where the nature of A and B were consistent with the statements that they made for both A and B. And that corresponds, if you use this method, to rows in the truth table that haven't been crossed out yet. And so the only row that's left standing is the fourth row. And so that means that that must be the solution to this problem. And so if I look, this corresponded to the scenario where P was false and Q was false. And so from that, we conclude that it must be the case that A is a knave and B is also a knave. And so that's a solution to this knights and knaves problem. Okay, we're going to do one more example. This is actually a slightly easier example. So same scenario, you're on the island of knights and knaves and you encounter two people, A and B. And A tells you, I am a knave, or B is a knight. And B says nothing. He or she keeps their mouth shut. And so we're supposed to use the truth table to determine, if we can, what type of people A and B are. So this is easier in a sense because we only have one statement to deal with, right? We only have the statement about what A says. Yeah. And so to outline the solution process, the first thing we're going to do is we're going to kind of give values or give propositions P and Q. Oops. For the nature of A and B. And then the next step, again, is going to be to translate A's statement and now we're going to fill out the truth table. And this time, because A was the only one that said anything, we're going to look for rows where A's nature is consistent with the statement that he made. And if we can find a single row where that's the case, then we've solved the problem. So what I'm going to do now is I'm going to ask you to pause the video and try to work out this problem for yourself, and then come back in a couple of minutes and we'll work it out together. Okay, so we're again going to make the association that P represents A as a knight, and the association that Q represents B as a knight. And then we want to translate the statement that A made. And so A said, I am a knave, or B is a knight. And so let's write that down over here where we have more room. I am a knave. And I'm going to give myself some more room than that. I am a knave, or B is a knight. And so if I break this down, A saying I am a knave corresponds to the proposition that A is not a knight. And so since P represents A as a knight, this is the negation of that. So that's going to be the negation of P. B is a knight is, we've already translated that, that's just represented by Q. And now we're joining these two things together with an or, and now we have to make a decision about what kind of particular or this is. The general rule of thumb is that when in doubt, unless it's very clear from the context that something should be an exclusive or, then you assume it's an inclusive or. And so in this case, I have no reason to believe that this is an exclusive or, so I'll assume that it's an inclusive or. Okay, and so I, ahead of time, already wrote that down in my column of my truth table, and so now I need to fill it out. And notice that once again, because this not P is a little bit more complicated than just P, I'm going to do a separate column of the truth table for not P and fill that out first, just to make sure that I don't make any mistakes in my head. And so if I fill out the column for not P, it's just going to have the opposite truth values in the column for P. So not P is going to be false, false, true, true. And now for the final column, I just have the disjunction, the inclusive disjunction of not Q and P. So I'm going to take the inclusive disjunction of these two columns. You remember, a disjunction is true if at least one of the two disjuncts is true. And so in the first column, Q is true. So I should get a true, not a false. My bad. So this should be true. In the second column, I've got P and not Q are both false. And so this is false. And in the third column, they're both true. So this is true. And in the fourth column, row. I keep saying column. I mean row. And in the fourth row, not Q is true. And so that means this is true. All right. So that was step 3. Step 4 is I need to go through and I need to compare the columns of the truth table corresponding to, since this was a statement that A made, I need to compare the truth value of A's statement and the truth value corresponding to whether A is a knight or not, and see if they're consistent. Okay, so in the first row, P is true. That means we're assuming that A is a knight. And the corresponding entry, I have a true. So that means the statement that A made is true, and that's consistent. That's okay. In the second row, P is true, which means A is a knight, but the truth value of the statement that A made is false, and that's inconsistent, so I'm going to cross that particular row out. In the third case, I've got P is false, so that means A is a knave, but the statement that A made was true, and that's inconsistent, so I'm going to cross that one out. And in the last case, P is false, so that means A is a knave, and the statement that he or she made was true, and that can't possibly happen. That's inconsistent, so I'm going to cross that out. And so if I look back, the only row in the truth table still standing is the first one, and so I know that this must be the state of affairs that solves this puzzle. And so if I look at the truth values of P and Q, this tells me that it must be the case that P is true and Q is true, which means that A is a knight and B is a knight. So that's my conclusion, is A and B are both knights. Okay, so we talked about the basic building blocks of propositional logic, the proposition, and we introduced 3 connectives, the conjunction and the inclusive and exclusive disjunction, as well as the negation. We learned about truth tables, and we got our hands dirty by solving some knights and knaves problems. In the next lecture, we'll come back and we'll add 2 new, kind of arguably more interesting connectives, the conditional and the biconditional, and we'll see how that opens up the possibilities of saying kind of more interesting things. All right, so next time.